Hi, so today we're going to discuss the AC source, an AC circuit containing a resistor, an inductor in an AC circuit, a capacitor in an AC circuit, and then combining the three elements, the RLC circuit, and then power in an AC circuit, and resonance in an RLC circuit, okay? And the transformer. And then we will discuss electromagnetic waves and the generalized Ampere's law, Maxwell's equations, Hertz experiment, and then we will derive the wave equation for electromagnetic waves, Doppler, and also Doppler effect for light, and energy carried by an electromagnetic wave, and also linear momentum carried by an electromagnetic wave, and radiation pressure. So we will discuss here alternating current circuits, which are circuits driven by a sinusoidal voltage known as an AC source, okay? And we will show that in this case, the current in each element in the series, such as the capacitor, inductor, or resistor, is also a sinusoidal function, like here, right? But it's not necessarily in phase with the applied voltage. It depends on which element is in the circuit, whether it's in phase or out of phase, and what's its maximum value. So this AC generator consists of a coil that is rotated in a magnetic field at a constant angular frequency omega, and this will generate a sinusoidal AC voltage that is induced in the coil, okay? So, and this voltage is given by this equation, which is V is equal to V max sine omega t, and V max here is the maximum output voltage of the AC generator, also known as the voltage amplitude. So the angular frequency of the generator is given by this equation. F is the frequency of the source and T is its period. For commercial power plants, they have a frequency of about 60 Hertz, which corresponds to an angular frequency of about 377 radian per second. So our aim in the following slides is that we want to find the amplitude and phase constant of the current. So the amplitude and the phase constant of the current in the circuit if we know the voltage amplitude and frequency, and also if we know the value of R or C or L, okay? So the first circuit we will discuss is an AC circuit containing a resistor, like this here. So if we apply Kirchhoff rule to the instantaneous voltage around the circuit, we have V minus VR is equal to 0, and this gives V is equal to VR equal to V max sine omega. So VR here is the instantaneous voltage drop across the resistor. And so the instantaneous current in the resistor IR is equal to V over R equal to V max over R sine omega t equal to I max sine omega t. So I max, the maximum current, is equal to V max over R. And so the instantaneous voltage drop across the resistor VR is equal to I max R sine omega t. And so as you can see, since both VR and IR vary with sine omega t, so they reach their maximum at the same time, which means they are in phase, okay? Also, this figure here is known as the phasor diagram. In this diagram, the alternating quantities, which are here the current and voltage, are represented by rotating vectors known as phasors. The length of the phasor represents the amplitude, which is the maximum value of each quantity, which is I max for the current and V max for the voltage. And the projection of the phasor on the vertical axis represents the instantaneous value of the quantity, which is IR or VR, okay? So for this circuit containing a resistor, the phasors lie along the same line because both are in phase. So they rotate together, they are in phase, okay? Also, a point to note here is that the average value of the current over one cycle is 0, right? And so the current is in the positive direction for the same amount of time that it is in the negative direction, and also has the same magnitude in both directions, okay? But the behavior of the resistor in response to this current is independent of the direction of the current, because the collisions between the electrons and the fixed atoms of the resistor will result in the heating of the resistor, right? And this increase in temperature depends on the magnitude of the current, but not on its direction. So the rate at which electrical energy is converted to heat is in the resistor is given by I square R, and I is the instantaneous current in the resistor, okay? Because the alternating current reaches its maximum value, I max, only for a brief instant in each cycle, it follows that heating effects produced by an alternating current with a maximum value of I max is not equal to the one produced by a direct current of the same value. It is less for an alternating current, okay? Also, an important value in an AC circuit is the root mean square, or RMS value, and it is given by I max over square root of 2 equal to 0.707 I max, okay? So this equation here states that the heating effect produced by a current of maximum value of I max is the same as that produced by a direct current of value I RMS, okay? And so the average power dissipated in a resistor that carries an alternating current is given by P average equal to I square RMS R. And also the RMS voltage is given by this equation, okay? And so an AC circuit of 120 volts, like from an electrical outlet, refers to the RMS value of the voltage, okay? And also note here that the equations for a DC current can be used for RMS values. And so for the resistor in the AC circuit shown, if VRMS is known, then the current in the circuit is given by VRMS over R. So let's consider now an AC circuit that consists of an inductor connected to an AC generator. If we apply Kirchhoff's rule to the loop, and since the induced electromotive force in the inductor is L di over dt, then we get V minus L di over dt is equal to 0. And so L di over dt is equal to V max sine omega t. So if we integrate if we integrate for the current, IL is equal to this equation equal to minus V max over omega L cosine omega t, which is equal to sine omega t minus pi over 2 times V max over omega L. So as you can see, the current IL and the voltage V, they are out of phase with each other by pi over 2 or 90 degrees, as you can see here. And so the voltage reaches its maximum value a quarter of an oscillation period before the current reaches its maximum value, okay? Or we can say that the current lags behind the voltage across the inductor by 90 degrees. So the instantaneous voltage drop across the inductor is VL is equal to L di over dt is equal to V max sine omega t equal to I max XL sine omega t. Okay? So let's consider now a capacitor in an AC circuit. So let's consider this capacitor connected to an AC generator and forming this AC circuit. So if we apply Kirchhoff's rule, we get V minus Vc is equal to 0. And Vc is the instantaneous voltage drop across the capacitor. So V is equal to Vc equal to V max sine omega t. And we know that Vc is equal to Q over C, right? So then we have Q is equal, so we substitute here and we get Q is equal to CV max sine omega t. And we know that the current is dQ over dt, and so we differentiate this equation and we get omega CV max cosine omega t, which is equal to sine omega t plus pi over 2, okay? And so the current is pi over 2 out of phase with the voltage across the capacitor, okay? And so the current reaches its maximum value a quarter of a cycle sooner than the voltage, as you can see here, okay? Which means that the current leads the voltage across the capacitor by 90 degrees. And so the maximum current is given by omega C V max equal to V max over XC, and XC, which is equal to 1 over omega C, is a quantity known as the capacitive reactance. Okay, and we can also write the RMS value, IRMS, is equal to VRMS over XC. And the same thing I forgot to mention about the inductor, so IRMS is equal to VRMS over XL, okay? So the instantaneous voltage drop across the capacitor is equal to V max sine omega t equal to I max XC sine omega t. So as the frequency of the circuit increases, the maximum current will increase, and this is because the reactance will decrease, right? And this is because the polarities of the plates will change more rapidly as the frequency increases, which will correspond to a larger current. And also, as the frequency approaches 0, the capacitive reactance approaches infinity, right? And the current will approach 0, which represents the DC condition. So the direct current condition is when the frequency approaches 0. And in the DC condition, no current passes through a capacitor in the steady state, right? So we will now discuss the RLC circuit, which is a circuit that consists of a resistor, an inductor, and a capacitor that are connected in series with an AC generator, okay? So the applied voltage is given by V is equal to V max sine omega t, and the current in the circuit is equal to I max sine omega t minus phi. And phi here is the phase angle between the current and the applied voltage. So the figure here shows the voltage across each element in the circuit versus time. So because the elements are connected in series, the current I everywhere in the circuit is the same at any instant, which means that the current has the same amplitude and phase at all points for a series circuit, right? And as we have seen from the previous slides, the voltage drop across each element is given by these equations, right? So as you can see, so these equations give the instantaneous voltage drop across each element. And you can see that the voltage drop across the resistor is in phase with the current, and the voltage drop across the inductor leads the current by 90 degrees, and the voltage across the capacitor lags behind the current by 90 degrees. Also, the total voltage across the three elements is the sum of them, okay? So because the current is the same in each element at any instant, and using the phase diagrams we obtained previously, so we may combine them into this figure here, okay? So as you can see, the vector sum of the voltage amplitudes VR, VL, and VC is equal to a phasor of length of V max that makes an angle phi with the current phasor I max, okay? So we have V max is equal to VR square plus VL minus VC square, okay? and we can substitute for the values here, and we get this equation. So the maximum current is then given by I max equal to V max over this value, and this is known as the impedance Z, okay, and its SI units is ohm, so it represents a ratio between voltage and current. So this equation is the generalized Ohm's law for an AC circuit, and it shows that the current in the circuit depends on the resistance, on the inductance, the capacitance, and also on the frequency, because these reactances here depend on frequency. Also, from this figure you can see that tan phi is equal to XL minus XC over R. So if XL is greater than XC, which occurs at high frequencies, then the phase angle is positive, which means that the current lags behind the applied voltage, okay? And if XL is less than XC, then the phase angle is negative, which means that the current leads the applied voltage. And if XL is equal to XC, then the phase angle is 0, and the AC impedance is equal to the resistance R, right? And the current then has a maximum value of V max over R. And the frequency at which this occurs is known as the resonance frequency, and we will discuss it further in the following section. So we will now discuss power in an AC circuit. So as we have seen earlier, if the AC circuit contains only a capacitor and a generator, the capacitor will be charged or discharged twice during each cycle, right? So the source will give charge to the capacitor during 2 quarters of the cycle, and this charge will return to the source during the remaining 2 quarters. And so the average power supplied by the source is 0, right? So equivalently, we can say that a capacitor in an AC circuit does not dissipate energy. And a similar process happens if the circuit contains only an inductor and a generator, then the inductor in an AC circuit also does not dissipate energy, okay? We have seen previously that the power delivered by a battery to a circuit is equal to the current times the electromotive force of the. So in a similar way, the instantaneous power delivered by an AC generator is the product of the generator current and the applied voltage. So for an RLC circuit, the instantaneous power P is given by this expression. So I times V equal to I max sine omega t minus phi V max sine omega t. But a more useful quantity is the average power over one or more cycles. So to find the average power, we first write this instantaneous power this way. By opening this here bracket, we get this expression. And then we take the average power of this quantity over one or more cycles. And note here that I max, V max, phi, and omega are all constants, okay? So the average value of sine square omega t is half. And this expression here can be written this way, and the average value of sine 2 omega t is 0, okay? So the average power is given by P average equal to half I max V max cosine phi, right? And in terms of the RMS current and voltage, we may write it this way. Okay, and cosine phi here is known as the power factor, okay? And if we use the phasor diagram shown before, this one, you can see that the maximum voltage drop across the resistor, so VR, is equal to V max cosine phi, okay? And we know that VR is equal to I max R. Okay, so from this expression we can find cosine phi, and then we substitute here cosine phi, and we get for the average power equal to I square RMS R. So this shows that the average power delivered by the generator is dissipated as heat in the resistor, just like in a DC circuit. And so no power is dissipated in an ideal inductor or capacitor. And if the circuit contains only a resistor, then phi is equal to 0 and cosine phi is equal to 1. And P average is equal to I RMS V RMS, okay? So we will now discuss resonance in an RLC circuit. So an RLC circuit is in resonance when the current has its maximum value. So the current IRMS is equal to VRMS over Z, which is equal to this expression. And because XL and XC are frequency dependent, the current is also frequency dependent. And the current is then maximum if XL is equal to XC, which is if Z is equal to R, okay? So the frequency omega naught at which this occurs is known as the resonance frequency of the circuit, and we can find this frequency from this equation. So we substitute for XL and XC, and we get this resonance frequency. So this frequency is also the natural frequency of oscillation of an LC circuit, as we have seen previously, right? So therefore the current in a series RLC circuit reaches its maximum value when the frequency of the applied voltage matches the natural frequency of the circuit, okay? So this is the frequency of the applied voltage, and when it matches the natural frequency of the circuit, we have maximum current or resonance. So also this frequency, at this frequency, the current is in phase with the applied voltage, okay? So this plot shows the RMS current versus frequency for a series RLC circuit, and you can see that the current reaches its maximum value at the resonance frequency omega naught, and the curve becomes narrower and taller as the resistance decreases. So this is R1 is less than R2, and it's a narrower curve. So this equation here shows that if R is equal to 0, then the current becomes infinite at resonance. But real circuits always have some resistance, okay? Also, we may express the average power as a function of frequency in a series RLC circuit. So we substitute for IRMS, and then we express this here in terms of omega and omega naught. Then we substitute and we get this expression, which shows that at resonance, when omega is equal to omega naught, the average power is maximum and is equal to VRMS square over R. So the plot shows that as the resistance is smaller, the curve is narrower, okay, near the resonant frequency, okay? So the sharpness of the curve is described by a dimensionless quantity known as the quality factor Q naught, equal to omega naught over delta omega, and delta omega here is the width of the curve measured between two values of omega, for which P average is half its maximum value, okay? So this plot here shows that high Q naught circuits, like this one, respond to a very narrow range of frequencies, while low Q naught circuits respond to a much wider range of frequencies. And one application of this circuit is the receiving circuit of a radio. So when the resonant frequency of the circuit matches that of an incoming radio, then the current in the circuit increases and the signal is amplified and given to a speaker. So the radio receiver resonant frequency can be varied and tuned to a different station, which means to a radio wave of a different frequency, by varying the capacitor in the circuit. So varying the capacitor will change the resonance frequency of the circuit, right? And also the receiving radio circuit is designed to be of high Q0 value so as to receive a specific clear wave, so a specific wave, a clear signal, and eliminate unwanted signals, okay? So we will now discuss the transformer. So when electric power is transformed over large distances, a high voltage and low current is necessary to minimize the heat losses I square R in the transmission lines, okay? When this power is received, it is required to be of low voltage and high current for the consumer. So the AC transformer is the device that can increase or decrease the AC voltage and current without considerable changes in the power delivered, okay? So it consists of two coils, like here, two coils of wire wrapped around a core of soft iron, okay? So the first coil is connected to the input AC voltage and has N1 turns, and is called the primary coil. And the coil here has N2 turns and is connected to a load resistor R and is known as the secondary coil. And the iron core serves the purpose of increasing the magnetic flux, right? And providing a medium where most flux through one coil passes through the other coil. So note also that the soft iron is used to reduce hysteresis losses. Also, heat losses due to the resistance of the coil wires usually are small, okay? So transformers have power efficiencies ranging from 90% to 99%. So in the following, we will assume an ideal transformer in which energy losses are zero, okay? So now suppose the switch in the secondary coil here is open, like here, and suppose the resistance of the primary coil is negligible. Then the primary circuit is equivalent to a simple circuit consisting of an inductor connected to an AC generator, right? And in this type of circuit, as we have seen previously, the current is 90 degrees out of phase with the voltage, and so the power factor that we discussed in the previous slides, which is cosine phi, will be equal to 0, and therefore because cosine 90 is equal to 0, and therefore the average power delivered from the generator to the primary circuit. So from Faraday's law, the voltage V1 across the primary coil is equal to minus N1 d phi b over dt, where phi b is the magnetic flux through each turn, and assuming no flux leaks out of the iron core, then the flux through each turn of the primary coil equals the flux through each turn of the secondary coil, okay? And so the voltage across the secondary coil, V2, is given by this equation. And since d phi b over dt is equal in both, we get this equation. So as you can see, if N2 is greater than N1, then V2 is greater than V1, okay? And in this case, the transformer is referred to as a step-up transformer, okay? If N2 is less than N1, the output voltage V2 is less than the input voltage V1, and the transformer is referred to as a step-down transformer. So if the switch in the secondary circuit is closed, a current I2 is induced in the secondary circuit, and if the load in the secondary circuit is a pure resistance, then the induced current is in phase with the induced voltage, right? And in an ideal transformer, the power supplied by the generator, which is I1 V1, is equal to the power in the secondary circuit, which is equal to I2 V2. The value of the current in the secondary circuit is determined by the load resistor R, so I2 is equal to V2 of so the current in the primary circuit is given by this equation. So if we substitute here, we get R equivalent is equal to N1 over N2 square R. And from this you can see that a transformer can be used to match the resistances of the primary circuit and the secondary circuit, right? And this way we get maximum power transfer between the source and the secondary circuit. So if the generator voltage is stepped up, the current in the transmission lines is reduced, which will reduce the I square R heat losses, right? Then the voltage is stepped down at the distribution station, and then it is finally stepped down to 120 or 220 volts at the customer's utility poles. So we will now discuss electromagnetic waves. So unlike mechanical waves, which require a medium to propagate, electromagnetic waves can propagate through empty space. Examples are visible light, infrared waves, radio frequency waves, and microwaves, okay? So first we will discuss the displacement current and the generalized Ampere's law. So we have seen previously that for symmetric current carrying conductors, the magnetic field created by the current can be found using Ampere's law, which is the closed integration of B dot ds is equal to mu naught I. And the line integral here is over any closed path through which the conduction current passes. And this conduction current is equal to dq over dt. So as you can see, Ampere's law includes only the conduction current, which is the current in a wire, okay? But Maxwell expanded this law to form the generalized Ampere's law, where he included another type of current known as the displacement current. So to understand the displacement current, consider a capacitor being charged as shown here. Okay, these are the two plates of the capacitor, and consider the two surfaces S1 and S2, which are bounded by the same path P. Okay, so according to Ampere's law, the line integral of B dot ds around the path P is equal to mu naught I, where I is the conduction current through any surface bounded by the path P. So for the surface S1, the conduction current through it is I, right? And so the right side of Ampere's law is equal to mu naught I, okay? But if we consider the surface S2, as you can see, the right side of Ampere's law will be equal to 0 because there is no conduction current passing through it, right? So there is a contradiction, and Maxwell solved this problem by adding a term known as the displacement current ID, and it is equal to epsilon naught d phi e over dt. So phi e here is the electric field flux, which is the integration of E dot dA. And so as the capacitor is charging or discharging, the electric field between the plates is changing and can be considered as equivalent to a current between the plates that is a continuation of the conduction current, okay? And so the generalized Ampere's law, also known as the Ampere-Maxwell law, can be written in this form. So the displacement current is added, and we get this expression, okay? So let's consider now the surface S here shown. The electric field through this surface, the electric flux through this surface is equal to EA. So A is the area of the capacitor plates, and E is the magnitude of the uniform electric field between the plates, okay? So if Q is the instantaneous charge on the plate while it's charging or discharging, then we have E is equal to sigma over epsilon naught equal to Q over epsilon naught A. And this result was derived in video 1 of Electromagnetism, so you can refer to that video for details, okay? And so we have phi E is equal to EA equal to Q over epsilon naught, and therefore the displacement current through S is equal to epsilon naught d phi E over dt, which is equal to dq over dt. So this shows that the displacement current ID through the surface S is equal to the conduction current, okay, I in the wires, okay? And so the generalized Ampere's law shows that a magnetic field is produced both by a conduction current and also by a time-varying electric field. So we will now discuss Maxwell equations. So Maxwell equations form the basis of all electromagnetic phenomena. And here we will consider Maxwell's equations in free space in the absence of any dielectric or magnetic materials, okay? So these are the equations. So the first equation is Gauss's law. The second is Gauss's law in magnetism. And it states that the net magnetic flux through a closed surface is equal to 0, which means the number of magnetic field lines entering a closed surface is equal to the number of lines leaving, which means magnetic field lines cannot begin or end at any point, right? And this implies that isolated magnetic monopoles do not exist. So the third equation is Faraday's law, which shows that an electric field is created by a changing magnetic flux, right? The fourth equation is Ampere-Maxwell's law, which shows that a magnetic field is created by a changing electric field and by an electric current, okay? So if one knows the electric and magnetic fields at a certain point in space, then one can find the force acting on a particle of charge q using this law, which is the Lorentz force law, okay? So Maxwell's equations, together with the Lorentz force law, describe completely all of classical electromagnetism. So as we will see in the following section, Maxwell showed that the third and fourth equations can be combined to obtain a wave equation for each of the electric and magnetic fields. So he showed that this wave consists of oscillating electric and magnetic fields, and that these changing fields induce each other. So the changing electric field induces a magnetic field, and the changing magnetic field induces an electric field, which maintains the propagation of the wave, okay? So in empty space, both Q and I are equal to 0. And the solution of these equations, of these two equations in this case, shows that the speed of this electromagnetic wave is the same as the measured known speed of light at that time, okay? So Maxwell unified electromagnetism and the field of light by showing that light is a form of electromagnetic radiation. So electromagnetic waves were generated by Hertz in 1887. His experiment consists of an induction coil connected to two spherical electrodes having a gap between them. So this part is the transmitter, okay? So the coil gives short voltage surges to the spheres, one becoming positive and the other negative. So if the voltage between the spheres reaches the breakdown voltage for air, then a spark is generated between them. And as the air in the gap is ionized, it becomes a better conductor, okay? And the discharge between the spheres exhibits an oscillatory behavior at high frequency. And so the apparatus then becomes equivalent to an RLC circuit, where the inductance is that of the coil and the capacitance is due to the spherical electrodes. So if we apply Kirchhoff's law to the circuit, you can show that the current in the RLC circuit oscillates in simple harmonic motion at the frequency of 1 over square root of LC. And for Hertz experiment, the frequency is of the order of 100 megahertz. So because the free charges in the transmitter circuit are oscillating, they are accelerating, and we know that accelerating charges emit electromagnetic waves, okay? So electromagnetic waves are radiated at this frequency of 100 megahertz. So Hertz detected these waves by using a second loop which represents the receiver, okay? So this loop is placed several meters from the transmitter, and it has its own natural frequency depending on its effective inductance and capacitance. So Hertz found that sparks were induced in the gap of the receiving electrodes when the receiver's natural frequency matches that of the transmitter. Okay. And so this way Hertz demonstrated that the oscillating current in the receiver was induced by electromagnetic waves radiated by the transmitter. So this experiment is analogous to a tuning fork responding to acoustic vibrations emitted by an identical oscillating tuning fork, okay? Also, in a series of experiments, Hertz showed that the electromagnetic waves generated exhibit the wave properties of interference, diffraction, reflection, refraction, and polarization, which are all properties of light. And so these electromagnetic waves are similar to light but differ only in frequency and wavelength, okay? And in one of his experiments, he measured the speed of this radiation using an interference pattern of these waves, and he found that the speed of this radiation was close to 3 times 10 to the power 8 meter per second, which is the known speed of visible light. So as mentioned earlier, Maxwell predicted that an electromagnetic wave consists of oscillating electric and magnetic fields. So the changing electric field induces a magnetic field and vice versa, which maintains the propagation of the wave, okay? And the E and B vectors are perpendicular to each other and to the direction of propagation as shown here, okay? So this figure captures the vectors at one instant of time. So as you can see here, we have chosen the electric field to be parallel to the y direction, the magnetic field to the z direction, and the wave is propagating in the positive along the positive x-axis, okay? So here both the electric and magnetic fields are always parallel to a certain direction, right? So in this case, the wave is said to be linearly polarized. So to derive the wave equation, we will assume a linearly polarized plane wave. So both E and B are restricted to be parallel to a certain direction, okay? And the plane containing the E vector is called the plane of oscillation. And so the wave is said to be plane polarized in the y direction, okay? So using Faraday's law, we have closed integration of E dot ds is equal to minus d phi b over dt. So let's consider a rectangle of width dx and height L in the xy plane. So we want to evaluate the line integral of E dot ds in the counterclockwise direction at the instant of time when the wave is passing through this rectangle, okay? So the integral for the top and bottom of the rectangle is 0 because E, as you can see, E is perpendicular to ds here. So for the right side of the rectangle, we have E x plus dx can be expressed approximately as Ex plus dE over dx when t is constant dx, and this is equivalent to the partial derivative of E to x, okay? And on the left side, the electric field is Ex. So we have for the closed integration is equal to Ex plus dx times L minus Ex times L. And if we substitute this, we get approximately L partial E by partial x dx. So also the magnetic field is in the z direction. So the magnetic flux through the rectangle, which has the area of L dx, is BL dx. And here we assumed dx to be very small compared to the wavelength of the wave, okay? So if we substitute, we get d phi b over dt is equal to this, and this is the partial derivative of b to t. And then we substitute this in this equation, and here this one here, and we get partial E by partial x is equal to minus partial B by partial. So in a similar manner, we can use Maxwell's fourth equation in empty space where I is equal, the conduction current is equal to 0, which is this equation, and evaluate the line integral of B dot ds around a rectangle in the xz plane of width dx and length L. So we have, in a similar way as before, this integration is equal to bxl minus bx plus dxl and is equal to this. The electric flux through the rectangle is equal to EL dx, and if we differentiate, we get this expression, and then we substitute here, and we get this expression. So partial B or over partial x is equal to minus mu naught epsilon naught partial E by partial t. So if we differentiate the equation we obtained in the first derivation with respect to x, which is this equation here. So if we differentiate it with respect to x, we get here this expression, and then we can change here the variables, and then we can substitute for partial b by partial x with this expression, and then we get finally this equation. And in a similar manner, we can get the equation for b. And both of these equations have the form of a linear wave equation with the wave speed v, which is named here c, given by this expression. So these are the wave equations for both E and B, and the value of the speed of this wave, if we calculate and substitute for mu naught and epsilon naught, we get 2.99792 times 10 to the power 8 meter per second. And this speed is exactly the speed of light in empty space. And therefore, Maxwell showed that light is an electromagnetic. So the simplest solution of these equations is a sinusoidal wave where both E and B vary with x and t of this form, okay? E max and B max are the maximum values of the fields. And this is the angular wave number, 2 pi over lambda, and omega is equal to 2 pi f. F is the frequency, the wave frequency. And we know that the speed of the wave is equal to lambda f. So if we, omega over k is equal to lambda f, and we name it here c, the speed of light. So the figure here shows a pictorial representation at one instant of time of a sinusoidal linearly polarized electromagnetic wave moving in the positive x direction. So if we take the partial derivative with respect to x for these equations, we will get we get these equations, and we know that partial E by partial x is equal to minus partial B by partial t, which is this equation. So we get this equation. And so at every instant, the ratio of the magnitude of the electric field to the magnitude of the magnetic field equals the speed of light. Okay, so this equation, the ratio of the amplitudes or the magnitude at any instant. So also note here that because the differential equations involving E and B are linear equations, electromagnetic waves obey the principle of superposition, which means that we can add two waves of the same frequency and polarization by adding the magnitudes of the two electric fields algebraically, okay? So we will now discuss the Doppler effect for light, where there is a shift of the observed frequency of the waves when there is relative motion between the source of the waves and the observer, okay? So as we have seen in another video, sound waves occur only in a material medium, and this medium is itself a frame of reference with respect to which motions of source and observer are measurable, right? But in the case of light, no medium is involved and only relative motion of source and observer is meaningful, okay? So the Doppler effect in light differ from that in sound, and we will discuss it in more detail in another video. But here we'll consider the case if a light source and an observer are approaching each other with a relative speed v, okay, then the frequency f dash measured by the observer, this f dash, is equal to square root of c plus v over c minus v f, and f is the frequency of the source measured in its rest frame, okay? So unlike the Doppler shift equation for sound, this Doppler shift equation depends only on the relative speed v of the source and observer, and is valid for relative speeds as great as c, okay? So if the source and observer approach each other, then f dash is greater than f. And if the source and observer are receding from each other, we need to substitute negative values for v in this equation, okay? An important application of the Doppler shift in electromagnetic waves is the measurement of shifts in the frequency of light emitted by a moving star or a moving galaxy. So light emitted by atoms were found to be redshifted, indicating that most galaxies are moving away from us, which means that the universe is expanding. So we will now discuss energy carried by an electromagnetic wave. So in another video, we discussed how mechanical waves carry energy. Electromagnetic waves also carry energy, okay? And this energy can be transferred to objects along its path. So the rate of flow of energy in an electromagnetic wave is described by the Poynting vector S. So S is defined is equal to 1 over mu naught E cross B. So the magnitude of S represents the rate at which energy flows through a unit surface area perpendicular to the flow, okay? So the direction of the Poynting vector is along the direction of wave propagation as shown here, right? And also since the Poynting vector represents power per unit area, its SI units is joule per second times meter squared or watts per meter squared. So for a plane electromagnetic wave, the absolute value of E cross B is equal to EB, and this is because E and B are perpendicular to each other, okay? So the magnitude of the Poynting vector is equal to EB over mu naught, and if we substitute for E or B using the relation E over B is equal to C, this one here, we get this expression, okay? And this equation applies at any instant of time, but for a sinusoidal electromagnetic wave, we are interested in the time average of the Poynting vector over one or more cycles. This quantity is equal to the intensity. So S average is equal to the intensity, defined as the average power per unit area, okay? So when we take this average, we will obtain an expression containing the time average of cosine square kx minus omega t, and the average of that is half. And so we get this expression for the intensity, which is E max square over 2 mu naught c is equal, also it is equal to CB max square over 2 mu naught. So we will now derive an expression that relates the intensity of an electromagnetic wave, or S average, to the average energy density, okay? So from the previous video on electromagnetism, we found that the energy per unit volume, which is the instantaneous energy density associated with an electric field, is given by half epsilon naught E square, and the instantaneous energy density UB associated with a magnetic field is given by B square over 2 mu naught. And since both E and B vary with time for an electromagnetic wave, then UE and UB also vary with time, okay? If we use the relation E over B is equal to E over C and C equal to 1 over square root epsilon naught mu naught, we substitute here and we get this expression for UB, which shows that UB is equal to UE. So the total instantaneous energy density U is equal to UB plus UE, equal to epsilon naught E square equal to B square over mu naught. So if this U is averaged over one or more cycles of an electromagnetic wave, then the total average energy per unit volume of an electromagnetic wave is U average is equal to epsilon naught average of E square equal to half epsilon naught E max square equal to B max square over 2 mu naught. And so the intensity I equal to S average is equal to C U average, okay? So we will now discuss momentum and radiation pressure. So electromagnetic waves not only transport energy, but they transport linear momentum as well as energy, okay? So if an electromagnetic wave impinges a surface, pressure is exerted on that surface. So suppose we have an electromagnetic wave that is incident normally, okay, at a surface, and suppose this wave transports a total energy T to the surface in a time interval of delta T. Okay, so and suppose the surface absorbs all this energy of T in this time interval. Then Maxwell showed that the total momentum P delivered to the surface is given by this equation equal to, so it's equal to T over C, okay? And the radiation pressure P exerted on the surface is defined as the force per unit area, so it's F over A, and we can use Newton's second law to substitute here for F, and we get we substitute then for the momentum and we get this expression, okay? And this quantity here, this one, is the rate at which energy is arriving at the surface per unit area, okay? Which is the magnitude of the Poynting vector, right? And so the radiation pressure P exerted on this perfectly absorbing surface is equal to S over C, okay? And so this is the expression for total absorption, and the average radiation pressure is equal to S average over C, which is equal to the intensity I over C for total absorption. We also can find the average power delivered to a surface of area A because S average is power per unit area, right? So the average power is equal to IA. Also, if the surface is a perfect reflector, then for normal incidents, the momentum delivered is in a time interval delta t is twice that for a perfect absorber, okay? So the momentum delivered for a perfect reflector is 2t over c. And this is because a momentum t over c is first delivered by the incident wave, and then the same momentum is delivered again by the reflected wave, the same way as for a ball colliding elastically with a wall. So the radiation pressure exerted on a perfectly reflecting surface for normal incidence is 2s over c, okay, which is twice that for a perfect absorber. So this pressure was measured using this apparatus shown here, and it has a value in the range of 5 times 10 to the minus 6 Newton per meter square, which is really small, right? And this apparatus is a torsion balance, as you can see, and the radiation pressure is measured by finding the angle through which this horizontal rod rotates, okay? And finally, for oblique incidence, for a total reflector, the momentum transfer is 2t cosine theta over c, where theta is the angle between the normal to the surface and the direction of propagation, and the pressure is 2s cosine squared theta over c. So in the following, I included 3 solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next videos.